When we talked about motion in Unit 1, we were very careful to choose rigid objects so that we didn't have to bother about things like change of shape. But more importantly, we could always forget about whether it was a spaceship, or a train, or a car, or even a person that was moving, and simply regard it as a fixed mass acting at a point. By making this somewhat sweeping assumption, we were able to produce some simple equations of motion which give a pretty good description of the way things move, or at least the way that certain things move. But can we really be sure that these simple ideas apply when we start looking at the motion of real objects in the real world? Or have we simplified the problem so much that it no longer bears any relation to the movement of real objects? In this program, we're going to examine the motion of some non-rigid objects. We're going to concentrate on motion in one plane, and we're going to see whether or not Newton's laws and the simple equations of motion still apply to these real-world objects. Let's start with an apparently simple motion. Once the jumper has left the trampoline, there's no external forces other than gravity. This acts only in the vertical direction. It's easier to follow the path of the motion if we have some reference point. So watch the white marker on the waist. The vertical direction is given by the white line on the screen. It doesn't matter where we put the marker, motion is always in the vertical direction. Now watch the black marker on her foot. But can we describe this motion? Well, the camera provides a very convenient time base, because every frame represents a time interval of 0.04 seconds. So if we look at every fifth frame, we have a time interval of 0.2 seconds. To simplify the process, we can put every fifth frame onto a computer in diagrammatic form. Let's do it. First, draw in a horizontal line to show where she's reached. 5 frames later, that is 0.2 seconds, she's reached here. 5 more frames, she's here, and so on. So these lines represent the height reached at time intervals of 0.2 seconds. Let's draw in some axes and plot the points. Here then is a graph of distance against time. But we know that the equation should be of the form s equals ut plus a half at squared, where s is the distance from the starting point, u is the velocity at the starting point, a is the acceleration, and t is the time from the start. Here, a, the acceleration, will be the acceleration due to gravity acting downwards. That is, a equals minus g. So the equation becomes s equals ut minus a half gt squared.
Unfortunately, it's not easy to apply this equation here because we can't easily measure u, the initial velocity. But it's not difficult to modify the equation to a more usable form. Another of the equations of motion is v equals u plus at. If we again substitute a equals minus g, then we get v equals u minus gt. So by rearranging this equation, we get u equals v plus gt. Now let's say that it takes time t dash to reach the top of the jump where v is 0. Then by substitution, u is equal to g t dash. So again by substitution, equation 2 now becomes s equals gt dash times t minus a half gt squared. And this equation should explain the curve that we've obtained. Let's see. This is the theoretical graph, and we can compare this with the graph from the analysis.
So this motion obeys our simple theory. But what happens if we make the motion a bit more complicated? But watch carefully. Some parts of her body still follow a straight line. But look at the motion of her foot. It's moving along a curved path, and so is her shoulder. This is somewhat unexpected, because Newton's laws say that a body should move in a straight line unless some external force is acting. To get these curved paths, we would need an external horizontal force to produce the sideways motion. So have our laws broken down already? Parts of the body seem to be obeying the laws, but others, like the foot and the head, aren't. So we need to look at the motion of separate parts of the body, or we need to find some way of representing the whole body by a point mass. This isn't such a revolutionary idea. Just think about rigid bodies. We were quite happy representing them by point masses. In other words, we were treating them as if the mass acted all in the same place. This idea may well be familiar to you as the center of gravity or center of mass. But how do you determine where the center of mass of a body lies? Well, let's have a look at this for some simple shapes. If we hang a shape by a point, the center of mass should lie somewhere vertically beneath the point of suspension. We can mark this vertical line by hanging a plumb line at the same point. The center of mass, then, should lie somewhere along this vertical line. If we now suspend the body by a different point, again mark in the vertical direction, the center of mass should lie somewhere along that line. Try with a third point of suspension. Again, mark in the vertical direction. And the center of mass will lie somewhere along that line. And I think you can see the point of intersection of all three lines must indicate the position of the center of mass. The same applies with an irregular shape. And as before, we have three lines intersecting at a point. The center of mass of this shape must lie there. Yet a third shape with a point of suspension here, the vertical marked by the thread. The center of mass lies somewhere along that direction. Suspend by one of the limbs. Mark in the vertical direction, the plumb line. So it must lie somewhere along there, or along there. Try the third point of suspension. Along that line there, or that line there. And here I think you can see we have a little bit of a problem. The lines are all pointing towards some point which lies outside the body. So the center of mass of a shape like this must lie somewhere in this region. So the important thing to notice is that the center of mass doesn't have to lie inside the body. Now what about human beings? Well, there were two problems. First, because we're in a regular shape, it's not easy to work out where the center of mass lies, even if we stand still. And secondly, human beings tend to move about and change their shape, so the center of mass is continuously moving. At this point, we need a bit of help from the computer.
I've programmed the computer so that it can calculate how the mass of a human being is distributed amongst its different limbs. So if we tell it where the limbs are positioned relative to each other, it will work out where the center of mass lies. On this picture, the center of mass is indicated by the star. Now watch how the center of mass moves as he raises his arm. And then, as he bends forwards, and as he bends backwards. The center of mass moves outside the body as he bends over. And this is quite a common feature of many irregularly shaped objects.
So maybe when we try to follow the motion of the trampolinist, we should be following the motion of the center of mass. the star indicates the center of mass. So if we draw our horizontal lines through the center of mass at 0.2-second intervals as before, we obtain this set of lines. Let's draw in the axes and plot the points to give a graph of distance against time. This is the same graph as we had before. So we can now see that our simple ideas of motion are obeyed, provided we talk about the motion of the center of mass. Now we might ask if this is true for all sports that involve jumping. As with the trampolinist, once the high jumper has taken off, there are no forces other than gravity acting on him. So if we look only at his vertical motion, he should be following the simple theory we've already established for the trampolinist. Because he changes his shape while in the air, we've had the computer work out where his center of mass lies. Again, the star represents the center of mass. Again, draw horizontal lines at 0.2-second intervals. Add the axes, plot the points, and the graph is as before, except this time we've taken it over the top of the trajectory. So as you can see, the vertical motion of the high jumper also obeys simple mechanics. Now, most activities involve motion other than that in a vertical direction. The high jumper has moved forward. So, of course, does the long jumper. Let's just check that her vertical motion is as before. Again, we'll use the computer to do the analysis. This initial part of the curve is as before. The second part of the curve is simply the inverse of this as she falls back to Earth. In other words, her vertical motion is exactly the same as the trampolinist. But you know that the long jumper is moving horizontally as well as vertically. Let's have a look at this horizontal motion. As before, the camera can be used as a time base. The lines showing her horizontal movement are approximately equally spaced, suggesting that she's moving forward at a constant speed. We can show this graphically by drawing in a set of axes and plotting distance moved as a function of time. Because the graph is a straight line, we can deduce that her horizontal speed is a constant. In other words, her horizontal component of velocity is a constant, which is what you might have expected if Newton's laws of motion are to be obeyed. Once she's taken off, there are no horizontal forces acting on her, and so she should move in a horizontal direction at constant speed. But what about her overall motion? Well, we can make use of the property of vectors, namely that the resultant is the sum of the horizontal and vertical components. Here are the vertical positions again, and here are the horizontal positions. So the path followed is like this. We can represent this graphically by drawing in a set of axes with the vertical component of motion labeled Sy and the horizontal component of motion labeled Sx. The graph represents the path followed by the long jumper in space during the jump, and we've calculated this trajectory by combining the vertical and horizontal components of the motion. Effectively, what we've shown here is that when we consider a more complicated form of motion, we can always treat the vertical and horizontal components separately. Because they're at right angles to each other, they don't interfere with each other. This is a very important idea in mechanics. Whenever we encounter a complicated form of motion, we resolve the motion into components at right angles, which are independent of each other. Each component can then be described by applying the simple equations of motion to the center of mass of the object. In this way, the problem is greatly simplified. So far, we've concentrated on how bodies move once they're in the air. But how did they get there in the first place? Common experience tells us that they push down on the ground. That is, they exert a force on the ground. This well-known experience is summarized in Newton's laws of motion, which essentially say that an external force is needed to change the motion of a body, and they then tell us how we can calculate this force. Well, if this force exists, can we measure it? The answer is yes. But first, let's just make clear exactly what forces do exist.
Suppose that you're standing still on the ground. You know that there's a force acting vertically downwards because of the pull of gravity. Now, if you represent a body by a point, and if the body is of mass m, then the weight force is mg, where g is the acceleration due to gravity. But if you're standing still and not sinking into the ground, then the ground must be pushing back on your feet with an equal and opposite force. This is the normal reaction force, called R.
Here's a piece of apparatus that measures this normal reaction force. It's called a pressure plate. Under the plate are a number of pressure gauges that give a small electrical signal when they experience a force. We can amplify the signal and plot the result on an oscilloscope. In effect, the pressure plate is just like a set of sophisticated and very accurate bathroom scales. Let's see it in operation. As someone walks onto the plate, you can see how the trace moves up. We're plotting the force against time, just like bathroom scales. If he picks up a weight, the trace moves even further up the screen, showing that the reaction force has increased because he's now holding an extra weight. So when the trace moves up the screen, the force is increasing, and when it moves down the screen, the force is decreasing. Now what happens when someone on the plate starts to move? Here's a very simple motion. You can see from the trace that the force is increasing and decreasing. Let's work out why.
To do this, let's think about just what forces are acting on a person when he moves. Now we know that no matter what the person is doing, the weight force, mg, is always acting. And furthermore, if the body isn't sinking into the ground, there must be a normal reaction force, just as before. But now suppose the person starts to move upwards. To move upwards, he must accelerate in that direction. But Newton's second law says there must be an accelerating force, which we'll call A. So the total upward force is now R plus A. So the effective normal reaction force is increased from R to R plus A when the person accelerates upwards. What about when he moves downwards? As before, we would expect the weight force and the balancing reaction force R to exist. But if he is accelerating downwards, then the acceleration force will also be downwards. This is equivalent to a normal reaction of R minus A. So when the body is accelerating upwards, the measured force increases, and when he is accelerating downwards, the measured force decreases.
So now you can understand why the trace is oscillating. The center of mass is alternately moving up and down. So the effective reaction force is going up and down. Up when he moves up, and down when he moves down. Now what happens when the weightlifter actually lifts a weight? How can we explain this trace? There are two distinct phases to this motion. First, the weight has to be accelerated upwards. Then, it has to be slowed down to stop the weight rising. So let's try and work out what forces we would expect. To understand what's happening, let's revise a little bit of theory. If we plot a graph of velocity against time for the movement of any object, then we can deduce the acceleration at any instant by drawing in a tangent to the curve. The slope of this tangent is the change in velocity divided by the change in time. That is, dv divided by dt. This is defined as acceleration. So if we have a velocity time graph, then we can deduce an acceleration time graph. As the weightlifter lifts the weight, the speed increases from 0 until it reaches some steady value. Then he slows it down in order to stop it overhead. So we'd expect the graph to look something like this. So we now measure tangents at different points. Hence we get a graph of acceleration against time. But Newton's second law says that the accelerating force is proportional to acceleration, so the force will be exactly the same sort of graph as the acceleration graph. This is precisely what we saw on the pressure plate. How big the bumps on the curve appear depends on how fast the weight is moved. If the weight's jerked rapidly, the curve might appear like this. At one instant in time, the net force measured by the pressure plate is 0. In other words, at one instant in time, we have a weightless weightlifter. Somewhat surprisingly, therefore, since human beings tend to move about a lot, their weight is constantly varying as they move their center of mass up and down against gravity. Even in simple operations like walking, their weight is varying, even though their mass is constant. All of the effects we've looked at involve motion in a straight line. Even the apparently more complicated motion of the long jumper and the high jumper can be resolved into two components of straight line motion at right angles. In all cases, this linear motion can be described by the simple equations of motion and by Newton's laws. Now, don't be tempted into thinking that all motions are in a straight line. Look at the movement of the trampolinist. Many motions involve rotation, and this is something we can't explain with our simple equations of motion. We don't look at rotation in this course, but you'll certainly meet it in later courses. Nevertheless, a great deal of the movement you see about you in everyday life can be explained in terms of the simple ideas we've talked about here. So next time you watch athletics, maybe you'll spare a thought for Isaac Newton.